Day 1 of our quantum computing series. I am Sarah Rachel, and in this series we are going to be starting from zero and build all the way up to real coding, real circuits and even quantum algorithms using IBM's Qiskit. Today's video is all about understanding the differences between classical computers and quantum computers in its simplest way possible. So now let's go into the video. Before we jump into today's topic, let me quickly walk you through this entire quantum computing playlist. So this course is designed for absolute beginners. Even if you don't know what is quantum computing or haven't heard this name before, let's start it together here. So here we are starting from zero and going step by step to the level where we code real quantum algorithm using Qiskit. So the course roadmap is here, like quantum versus classical computing. Here we will be understanding how quantum computing is different from what we use in every day and why that matters. Next is bits, qubits and quantum states. Here also we will be exploring some of the qubits and some of the states in quantum. Next are the essential mathematics that we need for quantum computing. So according to me, some of the prerequisites for this course would be learning mathematics such as vectors, complex numbers, linear algebra, and also you have to know Python, that is the base for our coding. Next is quantum circuits and logic gates. Here, logic gates are of different types, X, H, C0 and many other. You need not confuse all of them. It might be hard at the beginning, but we will make it simple in the upcoming videos. Next is superposition and entanglement. These things are the basic foundations of our quantum computing. So next is quantum measurement and probability. Here you'll be learning about how qubits collapse when measured and how probabilities play a huge role in quantum outcomes. Next is mastering the Qiskit and IBM Quantum Lab. Hands-on coding time is starting over here. Here we'll be setting up the Qiskit, write quantum programs and even run them on real quantum hardware. Some of the famous quantum algorithms such as the Grover search, quantum Fourier transform, all of these coolest algorithms will be handled here step by step. We'll be also checking out on some of the real-world applications such as artificial intelligence, cryptography and also chemistry-based applications that has the usage of quantum in them. Lastly, we'll be having a mini project where you will be using all those things you have learned so far in this course. This is just for the beginners, or it can be used if you're going to have some kind of ideas on what quantum is about. So now, if you're serious about learning quantum computing and want to go from beginner to someone who can already build quantum logic, stay with me till the end of the series. Make sure to subscribe and hit the bell icon and leave me the comments below after this video ends. So now let's go into the actual topic of today. Let's start with the big question. Why should you even care about quantum computing? Well, imagine this. You give a classical computer a very complex problem. It works step by step and eventually gives you an answer. But for some problems like simulating molecules, cracking some encryption codes, or solving certain optimization puzzles, even the fastest supercomputer take years. So quantum computers can solve some of these problems in just seconds. That's the superpower we are talking about here. So some fields such as AI, cryptography, finance, and even drug discovery and climate modeling could be revolutionized by this quantum computing. So you're not just preparing a cool topic, but also you're preparing for the future. So keeping that in mind, let's check what is the major differences between a quantum computer and a classical computer. Traditionally, we know transistors. Transistors are the building blocks of a modern computer. Like you'll be using on and off switches that make you sure that the electric current flows perfectly. Based on that, when these transistors shrink, automatically they move into smaller nanometers. Those nanometers make into smaller individual atoms. Thus, where your quantum mechanics starts working on. So, making this into account, all these processes may be done in parallel, making the processes being quicker and faster. Thus, there is a major difference between your classic and your quantum computers. So next, we'll be seeing about what is a classical computer. A classical computer works with bits either 0 or 1. It performs all the operation using these bits such as the logic gates and or not. Okay, before all these of things, let's go with an example. Why don't you take your laptop, your smartphone? All these run on bits. Let's say you open a photo. It's nothing but a combination of bits. Let's watch a video. Still, just billion of bits of zeros and ones played in a meaningful way. So classical computers are amazing, but they have few limitations. So generally we know that a bit is like a smaller unit of data in your computing method. So for instance, let me say that here you are having a normal computer where you would be having zeros and ones. The 0 and 1 can be represented as off and on respectively. These bits together can be dimensioned as 8 bits and 16 bits, where 8 bits is 1 byte and 16 bits is 2 bytes. All these bits are into consideration when you're going to check on audios or videos. All of those are made out of bits. Same wise, when you're going to be coming into a quantum computer, they use qubits. Qubits, we'll be discussing qubits in the upcoming videos very detailedly with the superposition or entanglement method. All of them are very important for this. For now, let's give an overview of it. Every single app that we use, like WhatsApp or YouTube, all have binary magic of zeros and ones. So you have to understand that zeros and ones are the bits that are being important for building all these. What does a quantum computer does? A quantum computer does not use bits, it uses qubits. As we have already seen, a qubit is a quantum bit. It has zeros and one as well, or both at the same time. So what does this same time? Same term means that is like you can have 0 or 1s at the same point of time. So that is called as a superposition. So that is another magic trick called as the entanglement, where two bits or qubits are connected in such a way that changing one affects the other, even if they are far apart. So to make it more simple, you can say that you are having a pair of 1 and 2. These two are going to be entangled. If you see that, in case your 1 is going to be having a combination of two colors. For example, if it's going to be having a combination of red at one side and blue at the other, and also your 2 is going to have red at one side and blue at the other side. So this is like if you have 1 is going to be your red color, then 2 is going to be a blue color. Or you can also say if 1 is going to be a blue color, then obviously your 2 is going to be a red color. Initially, it may be very confusing, but it is a very simple logic behind it. So I'll make a clear video that explains about entanglement and superposition. Entanglement is like when you have two or more bits that are going to be linked together, sharing the same fate regardless of the distance, enabling complex correlations. So like you'll be having some complex calculations, but your distance doesn't even matter, but they'll be linked together. Whereas superposition is that a qubit can represent the combination of zeros and ones until measured, allowing for a parallel computation. So like superposition means like you can have 0 or 1, or you can have both the numbers at the same time. So these two topics are very much important. So I'll be giving you other famous ball experiment called as the Schrodinger's cat. So that example will be the best one to explain this topic much more clear, so which we'll be seeing in the next video. So now for instance, you can just have a point of what is entanglement and superposition. Understand the qubit with a tiny bit of math. A qubit state can be written as alpha and beta. This alpha and beta are going to be the complex probability amplitudes, where alpha square plus beta square is going to become 1. So this means when we measure the qubit, we can get either 0, but until we measure it, it is in both the state as 1s. And how are these qubits created? Using the trapped ions, photons, or superconducting circuits, real science stuffs, but it is not so deep that we have to go into that first, but we are going to use the software called Qiskit to simulate all these easily. So just you have to know what is this qubits and how are these being used. So initially in a classical computer you have zeros and ones. So 0 and 1. So in a quantum computer, you will be using a method of mentioning these zeros and ones. This method is used or called as a bracket method. So a bracket method will be used for denoting the x, y and z, whereas this is going to be your x-axis, this is going to be your y-axis, and this is going to be your z-axis. All these axes are going to be measuring and checking out your qubits. So that is why upper you will be having a 0 and below you will be having 1. In case if you are not measured until both the states are going to be the same. Here we will be seeing an overall view or a comparison table of bit and qubits. So here a bit can be having 0 or 1s, where a qubit can be having 0 and 1 or in a superposition form. Next, here it will be a sequential method, whereas in qubit you will be having a simultaneous method, like it will be multiple parts that will be checking at the same time. Next, some of the gates in normal bits are AND, OR and NOT, whereas in qubits you'll be having X, H, Z and C naught. So let's see all those qubit gates in the next slide. So before that, the power that has been used in bit is limited by classical laws, whereas here it follows a quantum physics. Coming to quantum circuits. Quantum circuits are something very important. So, quantum circuits are the heart of the quantum computing method. Just like classical circuits have logic gates, quantum circuits have quantum gates. In Qiskit, we have to define a qubit, apply the quantum gates like X, H, Z, C naught and others. Then only we can measure the output. This forms the quantum circuit that we run either on a simulator or on an actual quantum computer. Let's take a look at this image of a quantum circuit. Quantum circuits are very important, so we have to understand what are the replications of a quantum circuits initially. So in this, you can see that you are having horizontal lines. These horizontal lines are going to be Q0 to Q3 in this instance, which are going to be taken as your qubits. Next, you will be checking around your H gates, Z gates and your, in this you can't say as XOR gate, you have to say it as C naught gate. So your Z gate is also a type of a gate that is to manipulate your qubit states. Initially, your H is going to be standing for a Hadamard gate. Hadamard. Your Hadamard gate, whereas your Z is also a part of your gate and C naught is represented as your XOR symbol. Remember some of the ways the gates have been represented. For example, let's take your Hadamard gate. It puts the qubits into superposition. So it will be putting it into zeros and ones at the same time. So that is called your superposition. Whereas your X gate, like it's going to be acting as a classical NOT gate which slip like zeros to ones or ones to zeros. So these things you have to keep it in mind before you check into your circuits. C naught gate is the control NOT gate. Flips a target qubit only if the control bit is 1. So these 4 gates are very much important. So based on that, now let's check the flow. Always check your flow from your left to right. So the circuit works from left to right just like reading. So qubits start from 0th state and the gates are applied in sequence. So initially your qubit will be in your 0th state. then you'll be applying the Hadamard gate. So this Hadamard gate is going to be placing zeros and ones. Each gate is going to change the state of the qubit. So for now, you can see that you have having a Hadamard gate that has been followed by a CNOT gate. So this kind of circuit can be called as the Bell state circuit. Bell state circuit. A Bell state circuit is like when you are having a Hadamard gate followed by a CNOT gate. The CNOT gate is this one. Bell state circuit is at the circuit of qubit of Q0 and Q3, where these two are being connected as an entangled way. So Q0 gets a Hadamard gate and becomes a mix of 0 and 1. Then C0 is applied with the qubit 0 as control, qubit 1 as target. So the final result of these qubits are going to be the entanglement. So that means if you measure one bit, the other automatically follows, even if they are far apart. So to understand this entanglement, you have to check on that cat example later on. So for now, this is the overall structure of your quantum circuit. Next, we'll be seeing about the programming of a quantum computer. You'll be amazed of how simple a quantum programming can be. With Qiskit, a Python-based toolkit, we create qubits and initialize the circuits, add gates to perform the operations, run it on an IBM's cloud simulator or real-time quantum chips. It's like writing code but for the future. And don't worry, I will guide you step by step in the upcoming videos. So initially, we will be defining the qubits and the circuit as well. So here there are types of Qiskit, Cirq and Penny Lane. These types of quantum programming languages use Python as the base. So this can be easily done by us, and also the simulation also of the qubits can be done easily. After we apply the quantum gates, we can measure and run it on a real-time quantum hardware or on a quantum simulator. So for this simulator, now we'll be using an IBM Quantum. Next, we'll be talking about the quantum chips. Quantum chips are where the magic happens. They look like something from the scientific movie like gold, layers of tubes, but really these chips are house qubits like gates and everything needed for a quantum operation. They run at temperatures close to the absolute zero to preserve the fragile quantum state. Like you have to know that your quantum computers will be in a form of a golden chandelier where it will be working in a very low temperature. So automatically your chip is also be going into an absolute zero temperature. We will be using an IBM Quantum Lab to run the real quantum programs without the needing of physical chips for now. So these physical chips operated in a temperature. Why do they do that? Because they maintain a coherence, and the main reason is to reduce the noise in them. Next, we'll be seeing about a real life example called the maze solver. Initially, when you're going to be having a maze, we'll be checking what are the paths that we can go through. Classical computer goes one path at a time. If it hits a wall, it backs up and tries another path. Obviously, this might take a lot of time. Whereas a quantum computer tries all the paths at the same time using the superposition and the inference method. You can check your image over all the infinite paths that are available to them. Based on the probability, they will be checking which is wrong and which is right. It cancels the wrong path and boosts the correct one. So this is exactly how you will be checking on a parallel vision if you are going to into a maze. Whereas in a classical, like you'll be solving Rubik's cubes by trying the continuous sequence patterns to solve that at a single phase of time. So automatically making the maze solving much more easier is done by a quantum computing. Thus, Google's quantum supremacy experiment worked in 2019. They also solved a problem in 200 seconds, which would take a supercomputer or a classical computer to solve in 10,000 years. The reason quantum computers have come into play in this technology era. So now, in this video, I hope you have understood what are the basics of quantum. So now, what are the key takeaways from this video? The classical computers are great for daily tasks. Quantum computers are better for complex, large-scale problems. Qubits are not just zeros and ones. They are powerful and flexible. Qubits are just not zeros and ones, but they can also be 0 and 1 at the same time. So mentioning the three main features such as the superposition, entanglement and the interference. Quantum computing is not a science fiction anymore, it's real and you're learning it. Don't forget to like, comment your questions and subscribe to continue this journey with me. If you have any types of doubt on this, you can definitely comment below and I will be there to respond to you. And also the entire PPT is available in the link in the description. Do check it and also follow this journey to know